Now we're thinking about velocity and the interpretation of graphs. Let's start by imagining a graph of some kind of variable. I just call it z versus time. Z could be anything. Right? And let's say the relationship between z and time shows up as a straight line on this graph. You know how to calculate the slope of a line like that. You pick 2 points. Fix this. You pick 2 points. Let's say this one, and get the time and z coordinates of both those points. Slope is just the amount of change in the vertical variable, z final minus z initial, this much change, divided by the corresponding amount of change in the horizontal variable. In this case, that's time. This much change. And we can write this in a more compact way. Final value minus initial value of anything, we always write as delta thing. So final minus initial z, just delta z. Final minus initial t, just delta t. This is the change in our variable z divided by the amount of time it took to make that change. This much change in z took this much time. So change in something divided by the amount of time it took to make the change is how you calculate a rate of change. The numerical value of this tells you how much change you get in z per second. Now, instead of just thinking about some variable that could be anything, calling it z, let's specifically imagine that that variable is location. So instead of z, we'll now call it x, our usual variable name for location. And so now the slope of the line is the final value of location minus the initial value of location. And we're treating those locations, remember, as vectors. So put the vector symbol over top. And that's now change in location. Change in location divided by the length of time it took to make that change in location. Of course, delta location is just another name for displacement. Displacement divided by the time it took to make that displacement. That's the rate of change in location. How many meters of change you get in the location per second. But we've seen this before. Displacement divided by the length of time it took to make that displacement is our definition for average velocity. But this was also slope of the line. So now we have a very, very important relationship, a relationship between slope of the line in a position versus time graph is this, but this is also velocity. So here's an important slogan that one needs to keep in mind all the time and be able to apply it. In a graph of position versus time, slope is this, but this is velocity. So slope is velocity in a graph of position versus time. change in something divided by the length of time it takes to make that change is rate of change, velocity is the rate at which position is changing. Slope in a graph of position versus time is the rate at which position is changing. The rate at which position is changing is just another name for velocity. Let's see what we can do with that idea. Slope is velocity in a position versus time graph. Let's say we have a position versus time graph that looks like this. From that, we can deduce what the corresponding velocity versus time graph would have to look like. Velocity versus time. And the behavior of the position graph changes at these 3 times. So there'll probably be some kind of change in the behavior of the velocity graph. So we want to line up those times so that it's easy to compare the position with the velocity graph. Okay. Here, during this first time interval, the object is moving towards more and more positive locations. That the direction of motion is positive. The final location is always more positive than the initial location. The final location is greater than the initial location. So the displacement is positive. And as we've seen before, direction of displacement is the same as the direction of average velocity. So this indicates a positive velocity. Or you could just as easily say, on a graph of position versus time, slope is velocity. Everything you say about slope is also a statement about velocity. Here in this time interval, slope is constant and positive, which means during this time interval, the velocity is constant and positive. During the second time interval, we've got a flat line. The slope of a flat line is 0. Slope is velocity, so the velocity is 0. Or you could just as easily say the location is staying the same all through this time interval. Location staying the same just means it's not moving. If it's not moving, the velocity is 0. Now in the third time interval, slope is negative and constant. And since on a graph of position versus time, slope is velocity, then constant negative slope means constant negative velocity. And the absolute value of this negative velocity, I want to draw so that it looks the same as the value of this velocity. Because these two I want to draw these 2 lines just about equally steep. In other words, let's say this and this are the same amount of time. And so in this amount of time, the object travels this far, from here to here. And then in this same amount of time, the object travels the same distance. So same distance per same time here and here, that means they both had the same speed. The velocities were in opposite directions, but the speeds were the same. And this length is the same as this length. This height is the same as this height, means that both of those lines are equally steep. That's an important thing to remember. It's just another consequence of how velocity is slope, That means that if two lines are equally steep, they will correspond to the same speed. Looking like that. Now, let's look at same kind of thing, a position versus time graph, and we'll see what the velocity graph looks like. But this time the position graph will be just a little bit more complicated. Here's the position graph. And here's the velocity graph. So in this first time interval, the slope is negative and constant. So the velocity is negative and constant. Here, during this time interval, the slope is negative and constant, so the velocity is negative and constant. Negative velocity all the time because the position number is always becoming more negative, indicating that the motion is always in the negative direction and displacement is always negative. Later values of location are always more negative than earlier values of location. So negative constant slope here means negative constant velocity, but a velocity with a higher speed. Like the slope, this negative slope is a more negative number than this negative slope. You might think of this as sort of a slope of -1, and then here's a slope of maybe -5, something like that. That. That is, in this case, the change in the vertical variable was small and the change in the horizontal variable was big. If you think of slope as rise over run, the rise was small, the run was big. Here, the change in the vertical variable was bigger over a shorter time. Rise was bigger, run was smaller, so that means a steeper slope. Or in this case, since slope is velocity, you traveled, during this part of the motion, you traveled a greater distance in a shorter amount of time, which means higher speed. And so the velocity is a more negative number. Here you might have been going just at a velocity of -1. That is, you move 1 meter per second in the negative direction. And here you might have a velocity of -5. That means you move 5 meters per second in the negative direction. And what we see comparing this and this is a little bit related to this. Equally steep means the same speed. Steeper means faster, higher speed. Okay, one last example. In these two cases, we looked at position versus time graphs, and we could deduce the velocity graph. We can use the same ideas the other way. We can look at a velocity graph and see what the corresponding position graph must look like. So let's think about this velocity graph right here. all positive velocities in this case. So some velocity for a while, and then zero velocity for a while, and then another velocity twice as big as the first one. And then what kind of position graph would we get then? Remember, on a graph of position versus time, slope is velocity. That is, these velocities tell you the slopes of this line. Since velocity is slope of a position graph, these velocities are the slopes here. So in this time interval, you have a positive constant velocity, which shows up as a positive constant slope on the position line. Here you have zero velocity, which shows up as zero slope. You're not moving at all, so you stay at the same location during this whole time interval. And now, a positive constant velocity bigger than before, which means a positive constant slope bigger than before. Like that. Now, one thing to notice, this tells you the slopes of this line, but there are lots of position lines that could all have the same slope, and therefore they would all correctly correspond to this. This only tells you the slope, it doesn't tell you the actual location. So you might have a position line like this with the same slope but passing through different locations. Same slope but different location. Same slope but different location. The numerical value of this velocity is the numerical value of this slope, and since this line is parallel, it has the same slope, in other words, the same velocity. These two lines are parallel, they have the same slope, which means they correspond to the same velocity. Any line that passes through any locations whatsoever, if it has this slope, it'll be a legitimate position line that corresponds to this. All three of those correspond to the same velocity graph. So the only idea that we're really dealing with here is slope equals velocity on a position versus time graph. And there are quite a few different things you can do with that fact. And we'll practice a whole bunch of them in class.